Okay, so let's see. The only kinds of reactions for which you have to write complete and net ionic equations are single and double replacement reactions. Okay? The only kinds of reactions for which you have to write complete and net ionic equations are single and double replacement reactions. Now, double replacement includes acid-base. So here's a single replacement reaction. Okay, so if we're going to write the products of this reaction, well, first of all, we need to know if this is going to be there's a driving force for this reaction. So we need to know on the activity series, is aluminum higher than nickel, or on the standard reduction potentials list, is aluminum lower than nickel. And if that's the case, then aluminum will displace the nickel, and the aluminum then joins up with the back of the compound. Aluminum will displace what it's like. Aluminum's a metal and nickel's a metal. And that's why this can happen this way. So we're going to put aluminum with the chlorine, and we're going to have nickel by itself. Now, nickel by itself is a solid. Okay, and we have to balance the formula, Al, with aluminum and chlorine. And aluminum, when you look on the periodic table, let's find, yeah, it is 3 plus, you're right. I'm just looking for your type of periodic table in this class. And so aluminum is in this column right here. Almost everything in here in the binary compound is going to be 3 plus. So 3 plus, and since chlorine is in this column here, okay, that'd be column 17, I believe it is, or 7A, then chlorine, all these chlorine is among those, has a negative charge, a 1 negative charge. And so to balance this formula, I need to have 3 chlorines, and so I have a subscript 3 here. Okay? Now we need to know if this is going to be aqueous or not. Okay? Say what?
It is.
Okay. Anybody disagree? All right, so chlorides are mostly aqueous. There are a few exceptions. You kind of find that, you know, lead, mercury, and things like that tend to be the ones that come back over and over again as far as forming a solid. But this is not one that forms a solid in this particular case. And so we're going to show this as being aqueous. Okay? All right. Now we need to balance the overall equation. So we're going to put our elements in a column here. We're going to make a grid. We use an atom inventory process in this class. And we're going to count all the elements. We've got 1 aluminum on the left, 1 nickel on the left, and 2 chlorines. On the right, we've got 1 aluminum, 1 nickel, and 3 chlorines. The only way to get the number of chlorines to be equal is if I multiply this side by, or this part here where the chlorine is located, by a 3, and this part by a 2. The result is that it's going to change on this side the number of nickels and chlorines, and on this side the number of aluminums and chlorines, or chlorides. So on the left now, the number of nickels I have is 3, the number of chlorines I have is 6. On the right, the number of aluminums I have now is 2. 2 times 1 is 2, and the number of chlorines I have is 2 times 3, or 6. Now we need to get the aluminums and the nickels the same, so if I have 2 aluminums on the right, to get 2 aluminums on the left, I just put a 2 here. That changes this to 2. And to get the number of nickels to be the same, I'm going to put a coefficient of 3 in front of the nickel, and that's going to change the number of nickels we have to 3. Okay? So now we have a balanced equation. To get a complete ionic equation, we're going to break up into separate ions anything that is an aqueous salt. Salt is just an ionic compound, okay, other than oxides don't tend to be salts, but almost any other ionic compound is a salt. The definition we learned about last week was a salt is, by definition, the product of an acid-base reaction other than water. And we can get this out of an acid-base reaction if we know enough about it to do it. And this too. So this is going to break up into separate ions because it's a salt that's aqueous. This is going to break up because it's a salt that's aqueous, or an ionic compound that's aqueous. Okay? So what we're going to do now is to write out all the anything that isn't aqueous, an aqueous salt is going to stay together. Anything that is an aqueous salt, we're going to break it up into separate ions. Now, breaking up into separate ions is just taking apart what we learned to put together when we're balancing these compounds. When we're learning to balance ionic compounds, we put them together in the ratio of their charges, just like we did right here. Aluminum with a 3 plus and a chloride with a 1 negative, we just put them together. Well, there's the basis for writing the complete ionic equation. So down here, we're going to write that we have 2 aluminums that are solids. We're not going to break them up because it's not aqueous. Okay, it's not an ionic compound and it's not aqueous. All right? We're going to break this one up. But I'll tell you what, just to be really, really clear, let's go over and do this one first because we've already got this one broken up. The way we balanced aluminum and chlorine was to look at the charges for aluminum and chloride and then choose enough chlorines here to balance out the 3 plus charge on the aluminums. Now breaking it up is almost the same. The only difference is now we don't just have 1 aluminum, we have 2 aluminum ions. Okay? So instead of 1 aluminum, we're going to show 2 Al3 plus. Instead of just 3 chlorides, we're going to have 3 times 2, or 6 chloride ions. Okay? The physical state of the ions is the same as the physical state of the compound in the problem. So if the compound is aqueous, these are going to be aqueous. In fact, since the only thing you break up are aqueous salts, anytime you have ions, they're always going to be aqueous. Okay? All right. Now let's go back and we'll do this one. Okay, so we have nickel, which has a 2 plus charge. Okay, now when we're talking about the elements that are here in the transition metals, these are almost always going to be 2 plus. These are almost always going to be 3 plus. And you really don't have to know these, but these along the top you kind of need to know. We've done a lab with all these, okay? When we're doing the salts with the, well, we didn't do all the charges, but we did some of them anyway. When we were doing the ions and magnets lab, remember that? Okay? Well, nickel is almost always going to be the same. It's 2 plus. And chlorine, we already know, is going to be a 1 negative. You could. Absolutely. Very good. Did y'all see how he did that? Okay? If chloride is 1 negative, and we have 2 of them, we've got to have a 2 plus on the nickel, don't we? Okay? All right. How many nickels do we have? 3. How many chlorides do I have? 6. Because I got 2 chlorines or chlorides in the formula times the 3, so I have a total of 6 chlorides. Now these are always going to be aqueous because the compound's aqueous. Okay, if you break it up, it's got to be because it's aqueous, and the ions are going to have that same charge. So this is called a complete, well, I haven't finished over here because I put that with the 3 nickels on the end over here. I didn't finish that part. Okay, so this is called a complete ionic equation. Okay, a complete ionic equation.
Why?
We have, why?
Why didn't we put the 3 and 9 to 2
Say what now?
The 3 and 9 to 2 or did you just leave it alone?
Oh, because it's not part of the this right here over here. Here it's a solid. It's not part of that. Yeah. Okay. Now, to make a net ionic equation, you write down anything that's not exactly the same on both sides. Okay? You just write out anything that's not exactly the same on both sides. So is there anything in this equation that is exactly the same on both sides? The chlorides. They're charged, one negative. They didn't change their charge. They're aqueous. There's 6 of them. So we're going to leave these behind. Okay? We're going to write down everything that isn't exactly the same on both sides. And the only thing that's exactly the same are the 6 chlorides. Notice nickel here and here, this is an ion. It's got a charge. This doesn't. This is aqueous, that's solid. They're different for 2 different reasons. They're different. Have the same number, but they're different kinds of species. Okay? The same with the aluminum. I've got a solid aluminum with no charge here. I've got an aluminum ion here with a 3+ charge. Now, metals, when they're by themselves, have no charge. In fact, any element in its natural state has no charge. Any element in its natural state has no charge. Okay? So, if we have oxygen in the form of O2, it's not going to have a charge because that's its natural state. If we have hydrogen in the form of H2, it's not going to have a charge because that's its natural state. Does that make sense? But it has to be an elemental form in its natural state. All right? Okay, so we're just going to write out 2Al solid plus 3 Ni 2 plus aqueous. We're going to leave out the chlorides. 2Al 3 plus aqueous plus, we're going to leave out the chlorides, 3 Ni solid. And this is a net ionic equation. Now remember talking about this last Thursday. These aren't really participating in the reaction. If they participated in the reaction, they would have changed. Because in chemical reactions, things change. That makes sense? So we call them what? Because they stay on the bench or sit in the stands? Spectator ions. Okay? They're spectator ions. Any questions about that? All right, so we just did some classwork with all these reactions. The only kinds of equations that you have to write net ionic equations for are double replacement, which would, by definition, include the subcategory of acid-base, and single replacement. Okay? And looking over this, it looks like all our single replacements, or potential single replacements, were no reactions, right? So I have two equations here for which you should be able to write net ionic equations.
Do you want to do that now?
Yes. Do that.